Hello everyone, my name is Mohammed. I'm a PhD candidate at the Civil Engineering Department at Lawrence Technological University, and today I'm going to give a short presentation about evaluation of innovative ducted bulk T-beam bridge system pre-stressed with 0.7-inch diameter carbon fiber composite cables. First, the problem statement. Precast pre-stressed side-by-side box beam bridge system as shown in this picture. Though widely used in bridge construction, they suffer from various drawbacks, such as extended construction time because of the cast-in-place big slab, also the development of longitudinal cracks between the adjacent beams, and no space is available to properly inspect the interior side of the box beams and provide adequate maintenance on time. In addition, steel strands where most of these bridge systems are reinforced or pre-stressed with are subjected to corrosion, specifically at harsh environments as shown here. In order to solve this problem, a new bridge system composed of ducted bulk T-beam is proposed with a proper gap between the beams that provide space for inspection. In addition, steel strands are replaced by corrosion-free carbon fiber composite cables, which are characterized by its lightweight and high tensile strength. This research involved the use of a large diameter 0.7-inch CFCC strands. Scope of the work. In order to study the performance of the proposed bridge system, a 1/2 scale ducted bulk T-beam bridge model was constructed, instrumented, and tested to study its flexure performance. As we see here, the bridge superstructure is composed of 5 ducted bulk T-beams, where the beams are joined at their top flange with 4 shear key connectors made of ultra-high performance concrete. This is a cross-section of an individual ducted bulk T-beam. The beam was pre-stressed with 3 CFCC strands at the bottom flange as we see here. The bridge model is being tested under different loading configurations, namely load distribution test, load cycling test, shear key test, and finally the ultimate load test. The construction of the bridge model started by setting up the decking platform at the Center for Innovative Material Research, CIMR, at Lawrence Tech University, then building the reinforcement cage, passing CFCC strands through the reinforcement cage, pulling CFCC strands using hydraulic cylinder and pump, then pouring ready-mix concrete and concrete curing, cutting CFCC strands using oxygen torch. After the construction of the 5 individual beams is completed, the beams were placed on steel supports with 3-inch gap between them. The formwork of the shear keys were built. The reinforcement of the shear keys were added. The components of the ultra-high performance concrete were mixed in the centrifugal mixer, and finally, the shear key joints were filled with ultra-high performance concrete, and this is the completed bridge model after casting the shear key joints. The bridge model was equipped with linear motion transducers, one underneath each beam, in order to measure the down roll deflection. In addition, electrical strain gauges were attached at the top of the beams around the loading spreaders in order to capture the concrete strains. These sensors are connected to a data acquisition system that provides a continuous monitoring of the bridge response. The first testing configuration is the load distribution test. In this test, each beam of the bridge model was loaded by a single point load of 30 kip at the midspan section as shown here. The load was applied using a 100-ton hydraulic cylinder which was connected to a hydraulic pump. This chart shows the deflection of each beam due to the 30 point load. The deflection values were used in order to compute the load distribution factors, which is, in other words, the proportion that each beam took from the applied loads. The second loading configuration is the load cycling test, where the entire bridge model was subjected to loading-unloading cycles under a 4-point loading setup as shown here. The test stopped after reaching 75% of the anticipated capacity of the bridge model, which is 130 kP. The chart here shows the load deflection curves for each loading-unloading cycle. The maximum deflection reached 9" at a load level of 130 kP. After finishing the load cycling test, the performance of the shear key joints were investigated by loading the exterior beam in the bridge model until localized shear cracks are initiated. The chart here shows the deflection of each beam while loading the exterior beam with 70 and 80 kP. It should be noted that the exterior beam was loaded to approximately twice its load carrying capacity without any noticeable shear key cracking. The final testing phase includes testing the bridge to failure by loading the intermediate beam using 2-point loading setup. The objective of this test is to estimate the ultimate load capacity of the bridge and the mode of failure. This testing phase is still in progress. The main conclusion drawn from the experimental investigation so far are: first, the surface and the post-cracking loads are transversely distributed in a pattern similar to that of the box beam bridge system with cast-in-place deck without any signs of shear key cracks or failure. Under loading cycles, the load deflection curves of the bridge model exhibited bilinear behavior with the cracking load marking the change in the slope of the curve. And finally, the ultra-high performance concrete shear key joints was found to be able to promote the integrity of the ducted bulk T-beam bridge system with the absence of a deck slab and transverse post tensioning. Thank you.